Just like we saw with human variation for anatomy, we also have physiological variation. And this refers to how the different body systems function uh, day to day, hour to hour, minute by minute, but yet how they function differently um, between individuals. All right, and so when we talk about physiological function, we're talking about things like blood pressure, heart rate, body temperature, the number of red blood cells, um, the rate of digestion, all that stuff. Things that you don't really have a lot of conscious control over, or any conscious control over. Things that your nervous system and the way that the systems are integrated, um, the physiology is automatically controlled. You don't have to do that. So let's take a look at what we call homeostasis. And it's very important that living organisms maintain what we call a stable internal environment. And this is important because in the outside environment, things going on outside of the body, those things are always changing. But yet, even though those things on the outside are constantly changing, the organism, in order to stay alive, has to maintain internal stability. And that's what we call homeostasis. It's that internal stability. Um, Again, that includes things like maintaining heart rate or adjusting heart rate in response to different conditions, breathing rate, um, blood pressure, body temperature, water balance, all of that is part of homeostasis. So to introduce you to the concept, I want to spend a few minutes going through an example talking about body temperature. You should have a handout number 3 or number 4, and it looks like it has a graph on it with some terms on it, so if you could find that. Alright, so let's find this handout here. So what we're going to do is we're going to plot a graph that shows the relationship between body temperature over time. So time is going to be our x-axis, body temperature, and we'll put degrees Fahrenheit. Typically metric systems use degrees Celsius, but so 98.6 degrees Fahrenheit or 37 degrees Celsius is average body temperature. Now, it doesn't mean that it has to be 98.6. Some people have a lower body temperature than others. Some people have a higher body temperature than others. That's that variation again. So what we want to do is we want to draw a line here, straight as I can, and this is what we call our baseline. This is the basic level where that parameter should be. So if we're talking about body temperature, that baseline would be 37 degrees Celsius or 98.6 Fahrenheit. And we don't want our body temperature to fluctuate too much around that. Now what we will see, let me change the color here. What we will see is this. We will see gradual fluctuations for every body parameter, regardless of what we're talking about. Gradual fluctuations above and below that baseline. Okay, that's normal. There's no way to keep a steady straight line. Things are always going to go slightly above and slightly below that baseline. This is important. This is called dynamic equilibrium. And that is a normal occurrence. It's just these slight fluctuations above and below that baseline. So what would happen then, what we're seeing is that body temperature rises just a bit, and it's above that set point, so events are occurring that cause the body temperature to go back towards the baseline, where body temperature is going to get lower. But what's going to happen is that that temperature is going to overshoot slightly, because by the time the body realizes the temperature is getting to where it needs to be, by the time those signals come in, it's actually going to be a little bit lower. Now, it may only be 1/10 of a degree here and there, and that's okay. But the point is that these fluctuations do occur. Now, a couple terms that you should be familiar with as it relates to these homeostatic mechanisms. Negative feedback. Negative feedback is important because negative feedback is what reverses the change that's occurring in the parameter. So again, if there's our set point, If our body temperature went way high like this, and let's say this was 103, well, the body's going to want to bring that temperature down so that we can get back to this baseline here. Well, how does it do it? Well, negative feedback plays a role. And negative feedback is essentially a process that reverses another process. So if something is causing the temperature to go higher than the baseline, negative feedback will negate that effect and actually cause the temperature to go back down towards the baseline. And what we'll find in these homeostatic parameters, in this homeostasis, it's all about negative feedback. It's all about reversing processes to make sure that these parameters, that these physiological events are all staying within the parameters set by the body to maintain that set point, to maintain that baseline. Now, there's also a thing called positive feedback. It doesn't happen as often, but it does happen, typically in disease states, but it can be a normal occurrence as well. Positive feedback results in more of the same happening. For example, if body temperature was climbing, positive feedback would then trigger more of the same. And as that body temperature continued to rise, that would trigger then more of the same. So in disease states, positive feedback is bad, but in other situations, positive feedback is good. For example, in labor and delivery, there's positive feedback involved in that. What happens is that as the baby stretches the uterus, that stretch on the smooth muscle of the uterus stretches at a certain point, which then sends a signal to the brain, which then stimulates the release of a chemical called oxytocin, which then stimulates contractions of the uterus. Well, as the baby is beginning to be moved out of the uterus, it continues to put stretch on the uterus, which then sends signals back to the brain, which then releases more oxytocin, which triggers more uterine contractions, which forces that baby out more, which causes more stretch, more feedback. That is a positive feedback loop. So we're getting more of the same. Negative feedback is we're getting an opposite. When one thing happens, negative feedback negates it and causes the opposite to happen. Now these are all really important in order to understand homeostasis. Let's take a look in here. This is in your book. This uses the example of a thermostat in your house. So the first thing that we would have is we have a certain set point, a temperature. So let's say we have our thermostat set for 68 degrees Fahrenheit. And this is wintertime. And so what happens is when the temperature drops to, let's say, 65 degrees Fahrenheit, the thermometer in the house senses that it's too cold. It sends a signal to the furnace to turn on. The furnace generates heat. We see a rise in temperature. The thermostat detects that temperature. Let's say it raises to 70 degrees. I'll put that here, 70 degrees. The thermostat detects that, shuts off the furnace, and now we're back to where we started. That is a negative feedback loop. So when the temperature got too cold, the furnace turned on, put heat in the house, raised the temperature, and when it got to a certain point, the furnace shut off, and now the room temperature is back to normal. Okay, that is what we call a negative feedback loop, and that negative feedback loop involves several things. It involves, in the human body anyway, it involves what we call a receptor. This receptor is detecting changes. It involves a control center or an integration center. And this is what receives the signals and processes those signals, or receives the signals from the receptors. It decides what to do. This would be our nervous system, our brain, spinal cord, brainstem. And then we have what we call an effector. An effector. This is what carries out the response. So, for example, you're cold, your body temperature drops, your thermoreceptors detect that change. They send those signals to the nervous system. The nervous system decides what to do, sends a signal to the effector. One of the things that happens is you get goosebumps, or you start to shiver, excuse me. And that shivering is involuntary skeletal muscle contraction that generates heat. There's also some other things that can happen. Your blood vessels near your skin can constrict to prevent less blood from going to that part of the body, and you're losing less heat through your skin that way. Either way, what's happening is that this idea is that we're trying to raise the temperature. Let's put this on a graph. So here's our set point. I'm going to say 98.6 Fahrenheit. And we're running along, dynamic equilibrium. All of a sudden we get really cool. Something happens and our body temperature drops. So what happens is, well, we get negative feedback. And it comes back up like this. So, well, what are we seeing here? Well, number one, we're seeing receptors detecting that the blood is getting colder. Number two, those receptors are sending signal to the nervous system, or the control center. And that's going to send out signals to do a variety of things. It's going to cause what we call vasoconstriction, which is going to prevent heat from leaving the body via the blood, so it's going to retain heat. We're going to see shivering, which is contraction of those skeletal muscles to generate heat. All of that then will help to retain heat and generate heat, and therefore bring that body temperature back up. Now, the vasoconstriction involves effectors, specifically smooth muscle in blood vessels, and shivering involves skeletal muscles. And one of the things that's important to note is that all effectors are going to be muscles or glands. Typically, they're going to be smooth muscle or cardiac muscle, or other glands, whether they're digestive glands, endocrine glands, what have you. Occasionally, skeletal muscles can get taken over under involuntary control in the case of shivering. So please make sure that you know the difference between an effector, a receptor, an effector, a receptor, the control or the integrating center. Know how they all work together in a feedback loop and how they can relate to negative feedback.